Hello all, I welcome you all to the third lecture for this course, E698M. First of all, I would like to apologize for the timing of this video. I was traveling and hence I was not able to record. I will make up for this time loss. From the next time onwards, we will have videos every Friday so that you will have enough time to go through the videos before we meet on the next Wednesday. Okay, so with that, let us proceed towards what I wanted to discuss during this video. So in the last lecture we stopped at a point where we saw certain consequences of the Drude model. So we showed that according to Drude's theory, you can explain DC conductivity to a certain way. For instance, he was able to prove that the current density J was proportional to the electric field E, and the proportionality constant was called as the conductivity, right? And then we found an expression for conductivity which turned out to be Ne square tau by m, and tau was called as the relaxation time constant. M was the mass of the electron, E the charge, and N is number of charge carriers. So this was found to match many experimental measurements where metals which had lot of carriers, lot of valence, turned out to be better carriers. But using the kinetic theory of gases, if one were to estimate or measure the resistances at various temperatures, so uh, this was measured by many. So I will quickly pull up the plot. So here we have a plot of resistivity versus temperature for a metal. There are certain things which the Drude's model was not able to clearly explain. One is the temperature dependent behavior. As temperature increases, the resistivity was measured to increase, and there is a prominent flattening of the resistivity values at low temperatures. This is not even related to superconductivity, mind you, that the resistance did not lower beyond a particular value as temperature is lowered. This is something which was not understood. This cannot be simply explained by the relaxation time or the scattering time constant model. And the second thing is you also have flattening at higher temperatures. So resistances also seem to flatten at higher temperatures. So these are some observations which were experimentally measured, and this cannot be simply explained by a single relaxation time constant tau, as Drude assumed. This is one thing. And the second thing which the Drude's model failed was that if you take the experimental measurement and then use the thermal velocity and then extract the mean scattering lifetime, and from there the scattering length L, it turned out to be about 10 angstroms, okay, something like 10 to 20 angstroms, which were the size of atomic separations in typical metals. And the mean scattering time which was experimentally measured was known to be something of the order of micrometers, or millions of atoms together, right? And not that the electrons scatter off the atomic ion cores. So that is something which was an experimental anomaly when we talk about Drude model. And the third important problem with the Drude model is that the Hall resistivity, which was shown to be always negative, and there were some metals which showed positive Hall coefficients. So all these things showed that there are some shortcomings in the Drude's model, and one needs to look at more sophisticated models which involves quantum mechanics, as we know. So today we will start to dig a little bit deeper into quantum mechanics. We will do a little bit of math. I want you to appreciate certain terms that we very normally use when we talk about quantum mechanics, these are things that I have used in the previous course 614 without giving a proper background. And that is something that I wanted to correct using this course, so that I give a proper background, we do some homework. The idea of quantum mechanics came with this wave particle duality, right? And this was because of two distinct experiments, as we saw previously. If I have a light bulb, right, and then I have a small slit and the second slit, and I have a detector. If the light is considered to be particle, as we saw previously, we are expected to see this behavior. If it's truly a wave, then we have interference, and then we get this, right? And one needs to know that this plot, that is the particle picture, comes when you sum up intensities, which is typically if psi of some r comma t is a wave, right? If you add intensity psi of r comma t square, this is the amplitude square, then you get this particle picture, because you have no negative component to this, right? So because this is why you will never have a destructive interference which will cause these dips or places where the light is totally absent. If you see in the particle picture, there are no place where the light is absent, right? So when you have the wave picture, you have places where you have complete destructive interference, and that is only possible if you add amplitudes directly, psi 1 and psi 2 of r comma t. So this is a true picture where you add wave amplitudes directly, giving you this constructive and destructive interferences where you have a bright and a dark spot, right? So this is something which is fundamentally different when you start counting particles or adding waves, right? When we thought that this is the right description of light, obviously we had the other experiment which we know as the photoelectric effect, right? So we have a cathode tube, and then another electrode pad placed close by, and we measure the current voltage versus voltage characteristics in the presence of light, right? Something like this, and we impinge light on through this, and we eject electrons from one electrode to the other, and then we see the current through this with relation to this photon. What we see is the velocity of the electron which is coming out of this electrode is not proportional to intensity, has no relation to the intensity of the light, but then has only relation to the frequency or the energy of the photon which is incident, the color of the light which was incident. So the velocity of the electron which comes out depends upon the color of the photon. The second thing is number of electrons ejected from the thing. It depends upon the intensity, of course, if you cross a particular threshold barrier, right? So it is these two aspects which made Einstein to think that your photons are not waves as thought by Huygens, but then it has to be packets of energy, and these packets of energy he thought to have some constant energy relation. Each packet had one constant energy, which was E h cross nu, and h cross is the Planck's constant, right? And nu is the frequency of the light, and actually h cross is the reduced Planck's constant, right? So h cross is h by 2 pi, right? So along these lines, these were the descriptions of a photon. However, there was another development by a nobleman. It's called de Broglie, who said that it is not only photons, all particles have wave-like behavior, right? And he gave an expression for this. It was P is equal to h bar k. Once again, h bar, the reduced Planck's constant, which was used in the context of photons. He told that it is not necessarily true that it can be used only for a photon, but then it is even for an electron. These were used because people were trying to understand why an atom was stable, right? So you have nuclei, some charged nuclei, right? And then they thought that the electrons had to go around these nuclei in circles. But then if you have electron which is moving around it, it has to radiate energy, and it has to radiate energy and then drop down. The rings have to constantly reduce, which were not reducing, right? The only way that you have a wave around this particle and still do not accelerate if you have standing waves. So you can have standing waves like this, which will go around the circumference and come back to the same point, right? So it can keep going it without having to change anything. So this was the thought of de Broglie, who came up with the fact that even the electrons should be waves. And then they have this kind of a relationship where k was called as the wave vector, or lambda, the wavelength, was written to be 2 pi by k, which was equal to h by p. P momentum, h is the Planck's constant and such, right? So if we describe a particle in the wave fashion, so typically, classically, waves were well known. And then let's say if we want to write or describe a wave by a function, it's called as wave function. A wave function is a mathematical term to describe how some amplitude of a particle or a wave or something varies in spatial domain as well as in time, right? So we write r comma t. So this is something which has been used for long. Psi is used in quantum mechanics. It's called as a wave function because it describes the amplitude of a wave, right? So let's say, for example, something which is traveling in space and time, right? How will you write a wave function which is traveling in space and time? We can write as, let's say, something as amplitude a, e power I, right? K dot r. This is something minus omega t. K is called as the spatial frequency, and omega is the temporal, right? So this is common classical mechanics wave behavior, right? But when we describe a particle using a wave description, as we just saw here, right, there should be some modifications or some additional constraints that you have to add to this wave description, right? And it was this idea that it was bothering many people. But then there was one guy who was called as Max Born, who came up with the idea that for a wave to describe a particle, it should have one important criteria, and that important criteria is that the integral of the mod square should be 1. And this mod square was the probability to find the particle. At time t, at position r, right? So this equation tells us that dq bar, right? So this equation kind of tells us that the particle should be found at each time t somewhere in the spatial domain, right? The particle exists, that you cannot have the particle has to be finally conserved, right? It cannot just vanish If it's an electron, electron has to go from one material to the other. It has to be transferred somewhere. You just cannot generate an electron, right? So basically, it is this principle that the probability to find an electron at any time t, the summation should always give 1. So this particular condition have to be enforced on any of the wave function, as we can call it, that if you want to use a wave function, it has to be normalizable. So this condition is called as the normalization condition. But just the example that we saw previously, right? Let's say a plane wave, instead of this r and t, let's come back to a very simpler definition, right? Something which is a plane wave in x, let's say a e power I k x. It is not normalizable, right? Because the integral diverges. So how do we solve for this? How do we work with such functions? The way to work with this is to use what is called as box normalization, which uses a mathematical technique which says that I enforce a tending limit minus L by 2 to plus L by 2 psi star x psi of x dx, which will turn out to be 1. So if I use this kind of a normalization, like if I have L which is expanding to a huge value, so I can always say that this psi is so small that if I add infinite such small values, I can eventually come to a value called 1. Right? So this is what is typically used when you have wave functions which are extremely large, or something which is completely oscillating, which is not localized at any point and such. Right? So now that we have already started to talk about probabilities, we are talking about what is the probability find an electron at some point and such, you have to talk about averages, right? So one particular example is, let's say, what is the average position of the particle, right? So let's say that I have a wave function which looks somewhat like this, which looks like a Gaussian, right? So this is 0 and then it has some width, right? So how do you describe a Gaussian? I'm going to write this psi of x to be like a e power minus x square by 2, and you can also write e power minus I omega t, but then let's say that we're talking about time t equal to 0, so this is just time independent, or at time t equal to 0. Okay, the wave function looks like this. I am arbitrarily taking a wave function which looks like a Gaussian, a normally distributed function. Example to normalize this particular wave function would be like let's say integral minus infinity to infinity a e power minus x square by 2, right, star complex conjugate of this a e power minus x square by 2 dx, right? So obviously both of them are being real, so you have minus infinity a square e power minus x square dx, which if you equate to 1, you can get an expression for a which will turn out to be integral e power minus x square is root pi, right? So this will be a square will be 1 by root pi, and a will be pi power minus 1 by 4, right? So the actual normalized wave function will be pi power minus 1 by 4 e power minus x square by 2 e power minus I omega t, right? So this will be but the question is, what is the most probable position? What is the most probable position? What is the expected position of the particle, right? A particle which is distributed in this fashion, what would be the most probable position? So to find the position, we once again use the statistical, the probability theorem, right? So how will you find the an expected value of x if you have the probability density function for x? You use this, right? Psi star of x psi of x dx. Right? This is what is commonly used when you have a probability density function and you want to have the average value of x. Now to find this, we can do this integration, right? So it is minus infinity to infinity a square x e power minus x square dx, and we know the value of a square is a constant, right? So minus integral minus infinity to infinity x e power minus x square dx will turn out to be 0. You can use this by substitution or do integral by parts. You will know that this one tends to 0. So whatever be the value of a square does not matter. So the expected value of x will turn out to be 0, in the sense that the particle is most likely to be found at the center of this Gaussian and less likely to be found elsewhere. Right? So this is just an example to show how a probabilistic view of a particle position can be used to know about the position of this particle. But before we proceed further, the typical approach to quantum mechanics would be now to throw the Schrodinger's equation, because we already introduced the wave functions. We just have to introduce these operators, and then you'll start getting solutions to these wave equations and such. But I would like to take a small detour and then do a little bit of math to understand what is a wave function, why do we use operators, and why do we talk about eigenvalues, why do we talk about eigenvectors, why do we talk about Hermitian operators and such, right? So we will take probably some 20-30 minutes now, and we will see some very interesting properties, and then we'll do some homework. We will understand why quantum mechanics was built in this particular fashion. So this is called the operator approach to it, and sorry about the mix up. The idea of operators were mostly by Schrodinger, and the idea of matrices was by the Heisenberg. But nevertheless, let's get back to to our discussion, where we are talking about wave functions, right? And let's talk about the general math of wave functions and the operators, and then we will see how it will gradually lead to the Schrodinger's equation, right? So let us talk about, let us say, a wave function psi r comma t, which has the following properties. It is defined everywhere, in the sense that for all r from minus infinity plus infinity, it has a well-defined value. It is infinitely differentiable everywhere, again, right? And all differentiable functions are continuous, right? So basically it is also continuous. So if we take these three conditions, and then we call the set of all functions which has all these three conditions, right? Like we call it, is typically called as L square, right? And because this is going to describe something which is physical, we have to add an additional constraint to this. So I take a set of such functions, a part of L square, and then I impose a condition on top such that it has to be square integratable, in the sense minus infinity to plus infinity psi of r comma t square dx should not go to infinity, should be a finite value, right? So if this is true, not equal to infinity, right, then we call the set of functions which satisfy all these conditions to be described by some set f, right? And it's easy to see that this f is a vector space. So what is a vector space? If I take two functions, let's say psi and chi, right? Psi plus chi eventually leads to something which is also a part of this vector space, right? And scalar multiplication, right? Psi plus lambda 2 chi also belongs to F. So given these conditions, this F, the set of all functions which are defined everywhere, completely differentiable, continuous, and also is square integratable, belongs to a vector space. Right? So with this given, let us define what is called as a scalar product of the wave function. The scalar product is also called as an inner product. I am sure you must have seen these things if you have taken linear algebra. But if I take a set of such functions and then define something like this, like if I take two functions as defined previously and write something within the square bracket separated by a comma. If I write this symbol, and this means that I integrate over space and make this R psi of R. Right? So this is the definition of an inner product. This definition has several important consequences. The first one is, if, of course, this psi and chi are both wave function, and hence they're all complex numbers, right? So typically wave function, let's say an example of a wave function in x is e power ikx, and already you have a complex number in this definition, right? The most waves does not necessarily have to have a complex number, but then they can be complex, right? So if we have something like this and I define psi comma something like this, it is the complex conjugate of this value, right? This is a single valued function and this is called a scalar product because it's an integral of this particular thing, right? While this is a complete function, right? This psi and chi are complete functions, but then the scalar product is a single valued function. It can be real or complex, right? But if I change the order of these particular wave functions, I get the complex conjugate, right? It can be easily seen from the definition itself. One. The second property is it has additive properties. I write something like this, or linearity we written as lambda 1 psi 1 plus lambda 2 psi 2, right? This can again be proved. The third property is if I have lambda 1 psi 1 right? Even this is pretty obvious. Now I have 4 and then an important property of the inner product space, that if psi comma turns out to be 0, and not the trivial case when both psi and chi are both zeros, right? They are non-trivial functions, right? Then psi and chi are called orthogonal wave functions. Right? This is why this inner product space is so important. There is a physical significance of this particular definition as well, but we will go to it later on. We are just thinking at this mathematically in an abstract sense, right? So right now, if I just define some mathematical function like this and then look at what are all the properties it brings out, we'll finally go back and then see what sort of physical intuition this definition gives. It is it's an overlap integral eventually, but let's just do the math first, right? So the fifth property of this is comma psi. If both of them are the same, right, it's always real and positive valued. Why? Because this will turn out to be mod of psi square, right? It's always positive value, and this is 0 if and only if psi is 0, right? Now let's go to the sixth, and the sixth property, also called as the Schwarz inequality, can be written as like psi square is lesser than equal to psi, sorry, right? This can be proved in a roundabout fashion, but this is called the Schwarz inequality or Cauchy-Schwarz inequality and such, which is used in many places, and this is of particular interest even for our discussions. We will use it later on in our derivations, right? So we define this inner product space which acts on a wave function or something which describes a particle, because we expect it to be square integrative, right? Now we define an operator. What is an operator? Because we keep talking about operators in quantum mechanics all the time, right? And we just talked about wave function. We defined an inner product for these wave functions. Now we define an operator, right? An operator is basically one which takes a wave function let's say psi, and converts or transforms into another. So what we mean by this definition is that, let's take, if let's say psi belongs to f because it is square integratable and such, all I'm saying is there exists, or we define, sorry, we define an operator, let's say a cap, such that a cap acting on psi gives us another wave function psi, also a function of r, right? At this point it needs to be mentioned that if this psi is a function is f, it does not necessarily mean that this also is f, but we won't go into that discussion right now, right? So all we are saying is we take an operator, work it on a wave function, it spits out another wave function. Whether it is square integratable or not, we are not going there yet, right? So this is an operator. An operator is something which works on a wave function. Now there are several properties of the operator is what we are going to see now. The first one being, if I have an operator a cap, and act on a linear combination of wave functions, right, which is lambda 1 being a complex constant, psi 1 wave function, right, plus lambda 2 a second variable, just a complex number, psi 2 of r, right? If it spits out lambda 1 a hat psi 1 of r plus lambda 2 a hat psi 2 of r, if this statement turns out to be true, we call the operator as linear. Till now it has all been little abstract, right? So let us give some give some examples, right? So now let's say I define a wave function, let's say psi of x, which is, let's say, like the Gaussian as I previously mentioned, or something, right? Some function psi of x. And if I have an operator x hat which works on psi of x, and then it just spits out x into psi of x. Remember, psi of x is a wave function. X into psi of x, x being a variable, x into psi of x is another wave function as we saw previously. So basically, this is the definition of x hat being an operator, right? If we have something like this, we can clearly see why this x hat is a linear operator, right? So if I have this x hat acting on a psi of x plus b psi 1 psi 2 of x, so x is just this one, right? A psi 1 of x plus b psi 2 of x, which will finally turn out to be a x, because x is just a variable, psi 1 of x plus bx psi 2 of x, right? So this typically proves that x hat, being just this very simple definition, is a linear operator. The second one is also, we can define something like d hat of psi of x, where d hat is a differential operator. I define this as dou by dou x of psi of x, right? And even here, if I, instead of psi of x, if I have a summation psi 1 of x plus psi 2 of x, dou by dou x is a linear operator, right? Normal generally. So basically this one will also be a linear operator. If I have a linear combination, it will also be a linear combination, right? So now that we have defined an operator, we show what an operator is, and then we have seen what is a linear operator. Now let's define what's a product of two operators, right? What is the meaning of a hat b hat acting on psi of r? What do we mean? What do we mean when we write something like this is, we first work this b hat on the psi of r. So we can distribute psi of r, right? And then we know that this one spits out a wave function. That's a definition of an operator, right? So a hat again can act on a wave function to give us another third wave function, right? And because it is defined like this, typically it is not true that a hat b hat acting on psi of r is not the same as b hat a hat psi of r, right? Because b hat acting on psi of r need not be the same as a hat acting on psi of r, and vice versa, right? So these two definitely does not have to be true. And because this is not true, you can define what is called as a commutator, a hat comma b hat, which is written as ab minus ba. Does not have to be square brackets, right? So this is called as a commutator. Let us work out a very simple example to understand what a commutator is and what a product is, right? Again, let's go back and use the same example as we saw previously. We are saying that x hat is something, psi is basically x psi of x, and d hat psi is basically dou by dou x of psi, right? So now what's a commutator? Commutator of x hat comma d hat acting on psi of x, as we saw in our previous description, this will be, this is not the square brackets, x hat d hat psi of x minus d hat x hat psi of x, right? And d x is small x, d hat is dou by dou x psi of x minus dou by dou x x psi of x, right? That's what we have defined here. And this will be x dou by dou x psi of x minus this, you have to use the product rule, right? X dou by dou x psi of x minus x, sorry, minus psi of x. This will turn out to be minus psi of x. So the commutator x hat comma d hat turned out to be minus 1 for x to be defined in the same way and d to be defined in what we have defined, right? So this was just a simple example to show how we can do operator arithmetics and how we can define some new operator based on the older operators, right? So basically we this commutator is a new operator that we defined based on the two operators that we had known previously, right? So now that we have these operators, let's say, right, now say we have two wave functions, right? Psi and chi. These are the two wave functions that we saw previously, right? And we saw that if A is an operator, A psi is also a wave function, right? And because A psi is a wave function, I can define an inner product space for this wave function, right? So if I write A psi comma psi, this will be a scalar product. We know that this will turn out to be a scalar product, a single valued function. And if we can find another operator, A dagger, such that A psi comma chi is equal to comma A dagger psi, right? So because these two are all, both of them are single valued function, they can be complex, they can be real, they can be anything, right? Now for any A, if we are able to find another operator, A dagger, right, we call the A dagger as the adjoint of A. It might seem very abstract right now, but then these have some very specific applications. If for some A's, A dagger also turns out to be A. So what we mean is A psi comma chi inner product is the same as comma A psi, right? You remember the definition of this inner product space? It's just A star, sorry, star psi, right? drq, right? So, and this is psi of r A psi of r drq, right? So if this is true, right, if the adjoint of the operator is the same operator, we call those operators as Hermitian. We will see some examples in our homework and then we will understand this much better. So these are all some very specific examples, and this operator theory is something that people study for a whole semester. So we just take some few aspects. So it might seem a little bit disjoint at this point, but we are just cherry picking few properties of an operator. We have cherry picked few properties of a vector uh, space, and we have cherry picked a few properties of what is called as an eigen equation, right? So right now we have defined what is an okay, so basically we defined what is a wave function, we defined what is an inner product space, right? We defined what is an operator, and we defined what is a product in the operator. We defined that we defined what is an adjoint if I have an operator, right? Something which inverts, right? So whatever which is on this side. I did not want to include bras and kets here. That's why I'm just using it in the wave function space. It's much easier instead of putting in all the bras and the kets, and then we have to talk about state space and all those things. So I'm not going there yet. So I'm just trying to keep it simple. So we have defined what is an adjoint. If the adjoint of the operator is the same operator, then we call it as a Hermitian. Right? And the Hermitian operator has few properties, which is particularly important for quantum mechanics and its applications. Right? So let's say yeah. So okay. With this, I'm going to take one step further and then define what is called as characteristic or eigen equations. So now let's just do another definition. Again, we are defining another operator. Okay, so let us consider an operator A, right? Something of the line of x, dou by dou x, or whatever, right? Some operator which operates on a wave function, something which is multiplied to a wave function, something which uh, transforms a wave function from one description to the other, right? And if there exists a function psi of x such that for any operator, okay, so I'm just taking an operator in random, and for that random I assume that I'm asking, does it exist, is there a function psi of x such that this operator A acting on the psi of r gives the same psi of r, but then which is just scaled, right? So if this is true, then we call psi of r as an eigen function of the operator A with an eigenvalue lambda. So basically what we mean is the operator, so previously what we saw is an operator transforms a wave function, right? It takes and acts on this wave function, and then we saw that A psi giving us phi, right? So here we are not saying that gives us phi, we are saying that A psi returns back the same operator, but then it is just scaled or rotated, or it is done. So it does not change the wave function considerably, it just makes it longer or shorter, right? Something, its projection is changed, that's all it's doing. So we call such equations as eigen equations, and for a particular operator we have what is called as the eigenvector and the eigenvalue. It is the complex value with which the vector gets scaled when the operator acts on it, right? So given this definition, if the operator A turns out to be Hermitian is something we defined previously, right? The operator is same as its adjoint. That's the definition for a Hermitian, right? If this is like we saw psi comma psi psi, this is the definition of a Hermitian. So if A is an Hermitian operator, then if we can find a wave function psi of r such that such an equation is true, then all the eigenvalues lambda are real. So this lambda previously is generally only complex. If A turns out to be Hermitian, then all the lambdas are real. We can prove this very simply. So I'm just listing out the properties. We'll either prove it in our homework or we will work out these examples later on in one of our lectures. Okay, so don't bother if I'm just throwing out sentences without actually proving them. They are not very hard to prove, right? So we are just using it so that just to save time, we are just taking, as I said previously, we are just cherry picking few properties of these operators, so that when we actually look at a Schrodinger's equation, we talk about the operator working on the momentum, the momentum operator working on the wave function, or the space operator working on the wave function, the or the Hamiltonian working on the wave function. I just wanted you to have a feel for what we are actually doing, right? So this is one property if A turns out to be Hermitian. And the second property is if we have two eigen functions, right, like psi and chi, as we saw previously for the same operator A, and A psi turns out to be lambda 1 psi and A phi turns out to be lambda 2 phi, then psi and phi will be orthogonal if lambda 1 is not equal to lambda 2. What we mean is our eigen functions of A. So this is this equation, this was it tells, right? So A acting on psi again gives us psi, basically means that psi is an eigenfunction of A. Similarly, phi is an eigenfunction of A, and they give two eigenvalues which are not the same, okay, which are non-degenerate. Then these two eigen vectors have to be orthogonal. So what we mean by orthogonal, as we saw previously, it is just that the inner product turns out to be 0, right? So we will stop this mathematical description now. We'll probably do some homework for us to give us a feel for all this math. The truth is there are much deeper operator theory which just handles only abstract values and nothing to do with physical interpretations. We have just taken few aspects which will be useful for our further understanding, right? Just to know why we call the Hamiltonian to be Hermitian, right? Why we want some of the operators to be Hermitian, right? So that we can actually do some operations. Why do we want the eigenvalues to be distinct? What does it mean if you have eigenvalues distinct, right? So that we know that the wave functions are orthogonal. Why do you need orthogonal wave functions? We have not gone into discussing basis and such, but I suppose you must have heard about basis in your linear algebra classes in your undergraduate. So here we stop. We will discuss further on with some practical examples. Okay, thank you.